Gravity assist, also known as gravity assist or slingshot maneuvers, is a technique used in space exploration to increase the speed and trajectory of a spacecraft without consuming fuel. In this sense, the art of planets or other celestial beings is utilized. When a spacecraft approaches a planet, it can use the planet's energy to change speed and direction while gaining power. The propulsion engine works as follows. When a spacecraft approaches a planet, it enters a puddle of sand created by the planet's mass. As the spacecraft flies past a planet, it is accelerated by gravity. More importantly, the spacecraft will also gain some of Earth's orbital momentum as it is pushed. After crossing the planet, the spacecraft continues its journey, but now it is faster and often takes a new direction that allows it to face the target. This will allow the spacecraft to save fuel and make interplanetary travel more efficient. Gravity assist is essential for deep space exploration. By carefully designing a spacecraft's trajectory and timing of its approach to the planet, mission planners can achieve astonishing distances and speeds that would otherwise require a significant increase in fuel consumption. For example, the Voyager spacecraft, which explored the outer planets in the 1970s and 1980s, used gravitational support from Jupiter and Saturn to gain enough speed to reach its destination and continue to the outer reaches of the solar system. Gravity assistance can also help move spacecraft to more distant destinations, such as the outer planets or even interstellar space. They allow scientists to explore multiple celestial bodies in a single mission. For example, the Galileo spacecraft used gravity assist to fly to Jupiter, and the New Horizons spacecraft used Jupiter's gravity assist to quickly reach Pluto. In a broader context, gravity assistants demonstrate the complex interplay between celestial mechanics and space travel. By harnessing the natural motions and gravitational forces of the planets, spacecraft can maximize their efficiency, explore remote regions of the solar system and beyond, and make significant advances in our understanding of the universe. Nuclear power offers great potential to improve the efficiency and capabilities of space travel. Unlike traditional chemical rockets, which generate thrust by burning fuel, nuclear propulsion systems use nuclear reactions to generate energy. This approach could lead to many potential applications, especially for deep space missions where efficiency and flight duration are critical. One of the major applications of nuclear power is interplanetary travel. Nuclear thermal engines work by using a nuclear reactor to heat fuel, such as hydrogen, and then releasing it to create thrust. This system can provide higher specific thrust, an important measure of propulsion system efficiency, than conventional rocket engines. As a result, missions to Mars or other planets can be accomplished in a much shorter time, reducing the time astronauts spend in space and reducing the problems associated with long missions. Another emerging application is the concept of nuclear power. This system uses nuclear reactors to generate electricity, which then powers ion thrusters. Although ion thrusters create a small amount of thrust, they are highly efficient and can operate for long periods of time. Such a propulsion system provides gradual, continuous acceleration, making it well suited for deep space exploration and ferrying cargo over great distances. A spacecraft powered by nuclear electric propulsion will eventually be able to reach significant speeds, potentially enabling missions to the asteroid belt and beyond. Nuclear propulsion also opens up the possibility of crewed missions to more distant objects such as the moons of Jupiter and Saturn. The ability to reduce travel time could make possible missions that are currently unattainable due to the limitations of chemical propulsion. This could also facilitate future resource-oriented missions, such as mining asteroids or exploring icy worlds in the outer solar system for signs of life. In addition, the reliability of nuclear systems provides another layer of benefits. Once launched, nuclear reactors can continuously generate power for long periods of time without the need for refueling, making them attractive for long-duration operations in space. Such durability could support research outposts or habitats on distant planetary bodies. As nuclear technology and safety protocols improve, the potential application of nuclear propulsion to space travel could revolutionize our exploration capabilities, allowing humanity to penetrate further into the solar system while optimizing efficiency and safety. Space elevators are a revolutionary concept that could revolutionize the way we access space and send resources and people into space. The basic idea is to build a structure that extends from the Earth's surface to a point beyond the Earth's stationary orbit, where gravity balances the gravitational force. This design is a strong rope or cable that is attached to the ground, and a weight is placed in the chamber to support the weight. Space elevators can offer many advantages. Currently, launching payloads into space requires a lot of energy and expensive chemical-powered rockets. Space elevators can reduce the cost of sending materials into orbit. This would reduce operating costs and increase capacity, which would benefit the economy and space. In addition to payloads, space elevators can perform a variety of tasks in orbit. With the development of transportation, industries such as space tourism, satellite launches, and even planetary exploration have flourished. Increasing the accessibility of space can facilitate the development of orbital infrastructure, including research stations, manufacturing facilities, and habitats, leading to an increased human presence in space. In addition, a space elevator would provide continuous or rapid communication between Earth and orbit, avoiding the long delays often associated with traditional launch schedules. This constant flow of cargo and personnel could be vital to keep long-term missions, such as missions to the Moon or Mars, running. Space elevators can also contribute to more complex space systems, such as solar-powered satellites that can collect energy in space and transmit it to Earth. While the concept of space elevators is attractive, several challenges must be overcome before they can become a reality. The materials used to make the cable must be strong and lightweight. To this end, new materials such as carbon nanotubes are being explored. In addition, it is important to overcome technical barriers related to stability, external forces such as weather and security measures. Despite these challenges, the concept of space elevators represents a revolution in access to space. If realized, they could change the way space is explored and used, making it more accessible and sustainable for future generations. Mining on asteroids presents both significant potential benefits and serious challenges as humanity searches for resources in space. The concept of mining minerals and materials from asteroids offers an innovative solution to replenish Earth's resources while providing the raw materials needed for space exploration and infrastructure development. One of the main advantages of mining on asteroids is the availability of large amounts of valuable materials. Many asteroids are rich in metals such as platinum, gold, and rare earth elements, which are critical for a variety of technologies, including electronics and renewable energy systems. Extracting these materials from asteroids could ease the pressure of resource scarcity on Earth, reduce the environmental impact of terrestrial mining, and potentially lead to new economic opportunities. In addition, objects from asteroids can aid future space missions by providing building materials, fuel, and even water for life systems in deep space. However, mining minerals from asteroids poses a major challenge. One of the biggest challenges is the technical requirements for finding, visiting, and removing asteroids. Space missions must first find suitable asteroids, some of which are small or orbiting far from the solar system. The development of efficient distribution systems, robotic mining technologies, and specialized remote control and mining systems is essential. The process of transporting the minerals to Earth or using them in situ is also a big challenge. Another challenge is the legal framework governing the utilization of space resources. Current international space treaties, such as the 1967 Outer Space Treaty, do not address the issue of ownership of property acquired from celestial bodies. Developing clear guidelines and agreements will play an important role in regulating commercial asteroid mining and preventing conflicts over space resources. In addition, financial considerations must be weighed. The initial investment in asteroid mining ventures is likely to be significant, and profitability may depend on overcoming technological barriers and making transportation and use of the mined materials cost-effective. There is also a need to define a market for materials extracted from asteroids, given the potential impact on existing terrestrial goods. Despite these challenges, the potential for mining on asteroids is truly exciting, as it could pave the way for a new era of resource utilization beyond Earth. As technology advances and understanding of the space environment increases, asteroid mining can not only provide essential materials for life on Earth, but also support a long-term human presence in space. This can foster innovation, reduce demand for terrestrial resources, and unlock the potential of the solar system for future generations. Protecting spacecraft and astronauts from space radiation is a critical consideration for long-duration space missions, such as those planned to Mars or beyond. Space radiation is high-energy particles emanating from a variety of sources, including the Sun and distant supernovae, that can pose serious health risks to astronauts. By penetrating biological tissues, these particles can cause DNA damage and increase the risk of cancer and other health problems. Therefore, effective radiation shielding is necessary to ensure the safety and well-being of astronauts during their long-term stay in space. One approach to shielding involves the design of the spacecraft itself. Engineers can design spacecraft using materials with high atomic numbers, such as lead or polyethylene, that can absorb or deflect radiation. In practice, this could mean incorporating walls of various materials into the spacecraft's design, creating layers that help mitigate the penetration of harmful particles. In addition, the spacecraft's layout can be optimized to place critical areas, such as living quarters, behind denser shielding or in science bunkers, places specifically designed to provide additional protection during solar particle events. Another strategy involves the mass of cargo and equipment inside the spacecraft as passive shielding. Cargo and water supplies can serve as effective buffers against radiation. This technique not only allows available resources to be used for a dual purpose, but also makes more efficient use of space inside the spacecraft. For missions to Mars, careful planning can ensure that the resources needed for the journey also help protect against radiation. Active shielding is another area of ongoing research that involves creating electromagnetic fields to deflect charged particles away from a spacecraft. This technology is still in the experimental stage, but researchers are exploring the possibility of using magnetic or electrostatic fields to create a protective bubble around the spacecraft. While this concept holds great promise, significant developments in technology and engineering will be required for its practical application. Finally, monitoring and timely reporting of radiation levels is critical to astronaut safety. Spacecraft could be equipped with radiation detectors that would provide real-time data on exposure to space radiation. Developing protocols to allow astronauts to take shelter in more shielded areas during strong radiation events, such as solar flares, could further reduce their exposure. As our deep space exploration ambitions expand, addressing space radiation will remain a priority. Combining innovative shielding techniques with effective mission planning and real-time monitoring will help us protect astronauts as they travel farther into space, opening up new opportunities for discovery and exploration. Recent advances in exoplanet imaging technologies have greatly enhanced our ability to detect and study planets beyond our solar system. As astronomers delve deeper into the study of these distant worlds, several advanced techniques have emerged that enhance our ability to image exoplanets and analyze their atmospheres. One of the most notable advances has been the use of adaptive optics in conjunction with powerful ground-based telescopes. Adaptive optical systems help correct for distortions caused by Earth's atmosphere and allow telescopes to produce sharper images. This technology is particularly useful for observing exoplanets, which are often lost in the glare of their parent stars. By minimizing atmospheric interference, astronomers can more efficiently detect and characterize light from exoplanets. Prominent observatories, including the Keck Observatory in Hawaii and the Very Large Telescope in Chile, have successfully used these techniques to obtain direct images of exoplanets. Another promising innovation is the use of coronagraphs and stargazers, which are designed to block out the light of a star, allowing the observation of nearby exoplanets. These instruments can selectively filter out starlight to detect planets that would otherwise go unnoticed. Upcoming NASA missions, such as the James Webb Space Telescope and the Rome Space Telescope, plan to utilize the advanced coronagraph technology. The James Webb Space Telescope's powerful infrared capabilities are designed to provide unprecedented insight into the atmospheres of exoplanets and possibly reveal the presence of molecules indicating habitability or even life. In addition, innovations in spectroscopic techniques have allowed astronomers to study the chemical composition and atmospheres of exoplanets. By analyzing the spectrum of light passing through or reflecting off an exoplanet's atmosphere, researchers can determine the presence of certain molecules, such as water vapor, carbon dioxide, and methane. The increasing accuracy and sensitivity of spectrometers is making a significant contribution to our understanding of the exoplanet environment. This is especially important for finding potentially habitable worlds, as analyzing the atmosphere can reveal conditions suitable for life. Finally, machine learning and artificial intelligence are playing an increasingly important role in processing the vast amounts of data generated by these advanced imaging technologies. These techniques can identify patterns and detect exoplanets with greater speed and efficiency, allowing for more discoveries and better characterization of known exoplanets. As these technologies advance, they promise to expand our understanding of the diverse planetary systems in the galaxy. Continued improvements in exoplanet imaging technologies have energized the field of astronomy and stimulated our efforts to study distant worlds. As we continue to improve these technologies, the ability to detect Earth-like planets and understand the conditions necessary for life becomes increasingly achievable. Advanced artificial intelligence systems have the potential to revolutionize space exploration and data analysis. As missions become increasingly complex and the amount of data collected during space missions grows exponentially, AI offers powerful tools to advance our understanding of space and improve performance. One of the significant contributions of AI lies in data processing and analysis. Space telescopes and satellites generate huge amounts of data, especially in fields such as astronomy and planetology. Advanced machine learning algorithms can sift through this data much more efficiently than traditional methods, identifying patterns, anomalies, and potential areas of interest. For example, AI has been used in the search for exoplanets, where algorithms can detect subtle signals in light curves that indicate the presence of planets passing through host stars. With these capabilities, scientists will be able to discover new celestial bodies at an accelerated pace. AI systems can also improve image analysis, which is critical for planetary exploration and satellite imaging missions. Technologies such as convolutional neural networks can process images from space to help identify geologic features, track atmospheric changes, or monitor environmental changes on planetary bodies. For example, AI has been effectively used to analyze images of Mars, helping scientists classify surface features and identify regions of potential scientific interest for future missions. Artificial intelligence-based systems could also improve the operational aspects of space missions. An autonomous spacecraft equipped with artificial intelligence can make real-time decisions based on environmental data, route optimization, and resource management. This capability is important for deep space travel, where communication with Earth can take significant distances. This intelligent system can analyze situations and make changes without waiting for guidance, improving flight efficiency and safety. In addition, artificial intelligence can improve the simulation and modeling of the space environment. By using advanced algorithms to model various scenarios, scientists can better understand complex systems and predict outcomes. Such modeling is essential for mission planning, risk assessment, and developing strategies for unforeseen problems during space missions. Finally, AI can facilitate collaboration between different scientific disciplines by combining diverse datasets from different sources such as geological, biological, and atmospheric studies. This interaction allows researchers to gain a more holistic view of celestial phenomena and contributes to the development of next-generation space exploration strategies. Advanced AI systems will play a key role in improving space exploration and data analysis. The integration of AI technologies, from accelerating data processing to enabling autonomous operations and sophisticated modeling, promises to open new horizons in the exploration of the universe, making future missions more efficient, informed, and effective. The potential applications of 3D printing technology for space colonization are vast and transformative, offering innovative solutions to the unique challenges of creating human habitats beyond Earth. This technology makes it possible to localize the production of components, tools, and even entire structures directly in space, minimizing the need to transport materials from Earth and making space missions more sustainable. One of the most significant benefits of 3D printing for space colonization is the ability to produce needed items locally using local resources. For example, materials found on planetary bodies such as regolith on the Moon or Mars can be used as raw materials for 3D printers. This process, known as in situ resource utilization, allows the habitat, infrastructure, and equipment needed for long-term missions to be built without relying heavily on supplies from Earth. By reducing dependence on materials shipped from Earth, mission costs and logistical complexities can be significantly reduced. 3D printing can also play a crucial role in creating repair parts and tools. Equipment malfunction is a common problem during long missions, and the ability to print replacement parts on demand can prevent delays and ensure continuity of operations. Astronauts will be able to fabricate specialized tools designed for specific tasks, increasing the efficiency and effectiveness of equipment maintenance and scientific research. Beyond structural parts and repairs, 3D printing technology opens the door to creating living systems. For example, researchers are studying how to print biological tissue and food. Imagine a scenario in which astronauts could produce new foods, improving nutrition and mental health during long-term missions. In bioengineering, research continues on how to use 3D bioprinting to create tissue structures, grow organisms that can support living systems, or recycle waste. Another application area is architecture and residential design. With 3D printing, architects can quickly create prototypes and complex structures optimized for the extreme conditions of space. Innovative designs can be developed that improve insulation, radiation protection, and structural integrity, ensuring that habitats can withstand harsh climatic conditions, providing a comfortable environment for future inhabitants. As 3D printing technology advances, its integration into space colonization efforts could eventually lead to the creation of self-sustaining extraterrestrial habitats. Such capabilities not only increase the feasibility of long-term human presence in space, but also pave the way for future exploration and utilization of the solar system's resources. By allowing astronauts to fabricate everything they need in their own environment, 3D printing opens up new possibilities for human development beyond Earth. Space solar power systems are an innovative concept designed to harness solar energy in space and transmit it back to Earth for use. The basic principle is to place satellites in orbit where they can receive solar energy without atmospheric interference or interruptions caused by weather or the day-night cycle. Solar-powered satellites typically consist of large arrays of photovoltaic cells that convert sunlight into electricity. Once solar energy is collected, it can be converted into a form suitable for transmission, often using microwave or laser beams. The energy is then sent to a special receiving station on Earth, where it is collected and converted into electricity for distribution on the power grid. The benefits of solar energy systems are enormous. One of the biggest advantages is the ability to continuously produce clean energy. Unlike solar power on Earth, which is limited during the day and dependent on weather conditions, space-based systems can receive solar power at any time of day. These sustainable investments can help alleviate some of the challenges associated with renewable energy, such as affordability and storage. In addition, solar energy in space can provide electricity to remote areas without a reliable electrical infrastructure. With the ability to transmit energy to multiple locations, These systems can provide a flexible solution for energy distribution, supporting humanitarian efforts, military operations, and emergency response initiatives. In addition, the deployment of space-based solar power systems can help reduce greenhouse gas emissions. By generating solar energy in space, the need for fossil fuel-based power generation can be reduced, which will have a significant positive impact on combating climate change. However, certain challenges must be overcome before space-based solar power becomes a reality. Building and launching large satellites, ensuring efficient energy conversion, and establishing reliable methods of power transmission is a complex and costly technological challenge. In addition, safety issues related to the health effects of high-intensity microwave beams or lasers require careful study and regulation. Despite these challenges, the concept of space-based solar power represents an interesting path to sustainable energy production. Continued research and development in this area could lead to breakthroughs that would allow for the efficient capture and distribution of solar energy from space, potentially changing the way our world is powered. Long-term human habitation in space presents a myriad of challenges that must be addressed to ensure the safety, health, and well-being of astronauts on long-duration missions, such as those to Mars or lunar outposts. Key challenges include microgravity effects, radiation exposure, psychological well-being, resource management, and sustainability of life support systems. One major concern is the physiological impact of prolonged exposure to microgravity. Due to the lack of gravitational influence, astronauts experience muscle atrophy and loss of bone density, which can lead to serious health problems over time. Potential solutions include the introduction of regular exercise using advanced fitness equipment designed for microgravity conditions. Researchers are also exploring nutritional and pharmaceutical therapies to mitigate these effects and keep astronauts healthy during long-duration missions. Radiation exposure is another important issue because astronauts are exposed to higher levels of cosmic radiation and solar particles on deep space missions than on Earth. This increases the risk of cancer and other long-term health problems. To solve this problem, spacecraft can be designed with more protective materials that are better at absorbing or deflecting radiation. In addition, the use of houses with layered walls or the use of natural materials such as lightweight stone or Martian soil for insulation could provide greater protection. Mental health is critical to mission success. Long flights leave crew members isolated, lonely, and stressed. The solution to this problem is to build social support systems and establish effective communication with groups on the ground. Creating shared spaces in living environments and engaging in recreational activities promote mental well-being. Research on team dynamics and conflict resolution is also important in preparing crews for the challenges of living together and working in confined spaces for long periods of time. Resource management is necessary to keep the site operational. Reliable water recycling, air purification, and food production systems are essential for longevity. Closed-loop living systems that recycle air and water minimize waste and resource requirements. Advances in hydroponics and aeroponics can help grow fresh food in space. Research continues on growing crops in microgravity and developing efficient food production systems, with potential lunar or Martian greenhouses that could provide not only nutrition but also psychological benefits for astronauts. Finally, the development of autonomous systems capable of repairing and maintaining the habitat will be critical. As we move further away from Earth, timely support becomes more challenging. Robotics, artificial intelligence, and automation technologies can greatly assist in repairing and monitoring life support systems, providing greater autonomy and reliability in the harsh environment of space. Addressing these challenges of long-term human habitation in space requires a multifaceted approach. By investing in research and technological advances, we can create a safe and sustainable home for astronauts on long-duration missions, allowing humans to explore the solar system and establish stability beyond Earth.